Hello everyone, I'm an AE from NOVOSENSE's sensor product line. I'm going to introduce how our MT6835 magnetic encoder performs its constant speed self-calibration. The system we're demonstrating today is a typical servo motor setup commonly seen, equipped with a built-in 23-bit optical encoder. The setup includes a controller, a motor with an internal optical encoder, and a magnetic encoder. The green cables here are the encoder feedback signal lines. Both the optical encoder and our magnetic encoder are connected to the controller. The yellow cables are the motor power lines. Here is the motor side on the shaft. We 3D printed a fixture and mounted a radially magnetized 2-pole magnet using a coupler. On the back of the PCB is our MT6835 chip. The other side features an MCU. The MCU converts the MT6835's SPI output into a universal serial interface recognized by the controller, ensuring accurate angle feedback from the magnetic encoder. Before starting self-calibration, let's first see how the servo system performs with the optical encoder. We'll start the motor and bring it up to 3000 revolutions per minute. On the host interface, we can observe the speed feedback from the optical encoder. At 3000 revolutions per minute, the speed fluctuation is around plus or minus 2.5 revolutions per minute. We'll use this as our reference data. Now that we've observed the baseline performance, let's look at the MT6835's behavior before self-calibration, using its default factory configuration. We disconnect the optical encoder feedback so the controller receives feedback only from the MT6835. After learning the zero position, we check its speed stability. With the motor again running at 3000 revolutions per minute, we can see the speed fluctuation is about plus or minus 40 revolutions per minute, noticeably larger than the plus or minus 2.5 revolutions per minute of the optical encoder. This is the MT6835's performance without self-calibration. Next, let me explain how to perform constant speed self-calibration on the MT6835. First, the motor must run at a stable, constant speed. The MT6835 offers 8 selectable calibration speed ranges. The factory default range is 400 to 800 revolutions per minute. Once the motor is spinning at a constant speed, the MT6835 can enter self-calibration mode via an enable pin. Pulling this pin high, typically controlled by an MCU, starts the process. For a demonstration, I'll simply use a jumper cap. During calibration, another pin outputs a PWM signal indicating the calibration status. 50% duty cycle means that calibration in progress. 99% duty cycle means that calibration is successful. And 25% duty cycle means that calibration failed. The entire process requires roughly 18 mechanical revolutions. Now, let's walk through the procedure. We reconnect the optical encoder feedback. Start the motor and pull the enable pin high with a jumper to enter calibration mode. We wait for calibration to complete, during which the PWM output can be monitored to track the status. Okay, calibration is now complete. Next, we'll test the system performance using only the MT6835's feedback. We remove the jumper, disconnect the optical encoder feedback, and let the controller receive angle data solely from the MT6835. We then perform zero position learning again to align the MT6835 with both the optical encoder and the motor's mechanical zero. After zero alignment, we run the motor at 3000 revolutions per minute once more. Now, with mount 6835 participating in closed-loop control after self-calibration, we observe a speed fluctuation of approximately plus or minus 10 revolutions per minute, compared to the plus or minus 40 revolutions per minute before calibration. The fluctuation range has significantly converged. This concludes the demonstration of the entire constant speed self-calibration process for our MT6835. Please feel free to contact us if you have any questions.